Welcome everyone. Today I'm going to talk to you about EVMPatch, our work on timely patching of Ethereum smart contracts using bytecode rewriting. My name is Rodler. I'm from University of Duisburg-Essen and is a collaboration with NEC Labs Europe. Now, when we started this project, we really had one question. How do you protect a smart contract after deployment? Right? So imagine this, you develop your smart contract, you deploy it to the blockchain, you have a lot of users interacting with your smart contract, and then you find out it has a security issue. What do you do then? In a traditional software setting, you would say, why don't you just deploy a patch, right? But in Ethereum and many other blockchain platforms, smart contracts are immutable, so they cannot be changed after they have been deployed. Now, we have a lot of prior work on vulnerability detection, right? So before you deploy a contract, you should really use all of the tools available to test your contract and to verify that it works correctly. You can use symbolic execution here, you can use static analysis here, dynamic analysis, and so on. But the problem is, assume you deploy your contract, right? So, and now 2 months later, some new symbolic execution tool is released and it finds a vulnerability in your contract which no tool has found before. What do you do then? You have already deployed your contract. Bad luck. Also, we observe a lot of incidents on the blockchain, and for those incidents, many of the smart contracts don't really include any plan on how to react to incidents, right? So there is no strategy for patching, no strategy to deprecate the contract. Sometimes contracts are even used months after public bug disclosure, right? So we need to enable smart contract developers to patch new issues that have been found after deployment of the smart contract. Now, there are some strategies on how you can patch your smart contract. So the Ethereum community came up with two primary strategies here. We have the migration strategy, where you deprecate your old contract, you deploy a new contract, which is a patched version of your contract, and then you manually migrate the state from your old contract to your new contract. So you have to develop your smart contract in a way such that it supports this migration, and the migration itself is usually done by a developer. Now there's a second pattern. You can actually achieve an upgradable contract using a special code pattern, which is called a proxy contract pattern. So the idea here is you split your contract into two parts. Immutable proxy contract, which forwards all transactions simply to the logic contract. And the proxy contract is immutable, is the public face of your contract, and the proxy contract can switch to a different logic contract. So you, as the maintainer of the smart contract, you can issue a switchover transaction and tell the proxy contract to switch to a new logic contract. Now, the problem here is you have to manually convert your contract to use this pattern, right? So this is not trivial to write a good proxy logic contract pair. And additionally, you have to ensure a thing called storage layout compatibility. This means you have to ensure that once you deploy a second logic contract, it really uses the same storage layout. And remember, the storage is basically the hard disk of your smart contract, so it stores all persistent state. And if you deploy a new logic contract, it uses the same storage address space. So really, they have to ensure the same layout inside of the storage address space. In practice, this means you can't really change any data types, any data structures when patching the logic contract. Now, this sounds quite nice, right? So you can, one switchover transaction, then your smart contract is patched. You don't have to change your address. You don't have to notify your users that you have changed your smart contract and so on. So this sounds good, but is this really practical? We performed a study with 6 developers, and 4 of those actually had a production-grade smart contract experience. And we asked them to do various tasks. Manual patching of smart contracts, but also actually creating an upgradable contract. So we gave them an existing smart contract, and we told them to convert this to an upgradable contract and to use the proxy pattern. The notable thing here is actually none of the developers managed to create a fully functional upgradable contract. Now, what can we conclude from this? So currently, smart contract upgrading is really cumbersome. It's time consuming. If you use the migration pattern, you have to do all this manual migration, and it's error prone. If you use the proxy pattern, you really have to make sure that everything works correctly. Now, this is nothing that you want with a smart contract that might handle millions of dollars, right? So we really need some automation here. And with this, I'd like to introduce you to EVMPatch, our fully automated patching framework. So EVMPatch really automates the full patching process. EVMPatch automatically converts a contract, a stock Solidity contract, to use this proxy pattern. And it also automates the deployment of the contract and all future upgrades. EVMPatch also automatically introduces patches using bytecode rewriting. So we use a template-based patching approach here with a custom domain-specific language that expresses the patches. And this way we can naturally preserve the storage layout and ensure compatibility of all logic contracts. But you don't have to trust the bytecode rewriter. We have a differential patch testing component which ensures that the behavior of the original and the patch contract is equivalent. Now let me walk you through a typical workflow with EVMPatch and also the architecture of EVMPatch. Now we have a developer, and this developer is responsible for a smart contract. And the developer might start some vulnerability detection component. So this can be really any analysis tool. So this is only very loosely integrated into EVMPatch. It can also be a manual vulnerability report, right? So if some responsible disclosure process gives the developer information about a vulnerability, then the developer can simply pass this on to EVMPatch. The important part here is EVMPatch receives a machine-readable vulnerability report and then uses this vulnerability to patch the vulnerable contract bytecode. EVMPatch selects a right template for the patch and applies this template to produce the patched contract bytecode. This patch contract bytecode is now passed on to the patch testing component, where we replay all of the transactions that are recorded on the Ethereum blockchain. And we ensure, using a differential testing approach, that the behavior of the original and the patch contract is the same. We do omit some low-level execution details, but we really ensure that behavior in terms of state updates, external calls, ether transfers, and so on is the same. If the patch testing succeeds, then we can deploy the newly patched contract bytecode as a new logic contract of our upgradable contract. Now, if the patch testing fails, then this can have two reasons. The vulnerability detection actually reported a false alarm. So this was not really a vulnerability, and we accidentally patched something which is not really a vulnerability, and then we broke the functionality of the contract. The second case is when this is a true vulnerability and the patch tester detects that the patch prevents a prior transaction, then we can conclude that this is an attack transaction. Now, in any case, we need to notify a developer of this. Let me walk you through EVMPatch's bytecode rewriter. So we patch on the bytecode level. So here you can see parts of a control flow graph of the EVM bytecode. And here we have a vulnerable multiplication instruction. Right? So this multiplication instruction is vulnerable to an integer overflow. So we really need to insert here a checked multiplication. Now, the bytecode rewriter keeps the code layout of the original contract intact in the rewritten contract. So basic blocks that are not changed, they are simply copied over, and they are also at the same address. basic blocks that need to be patched are replaced by trampolines. So in this case, the basic block at hex AB is replaced by a trampoline, which jumps out to the end of the original smart contract bytecode. And there we can insert as many new instructions as we like. This means here we can replace the vulnerable multiplication instruction with a checked multiplication patch template from EVMPatch. Then we simply jump back to the original code and have concluded the bytecode rewriting. Now, we performed evaluation of the attack detection capabilities of EVMPatch. We evaluated on 5 known to be exploited ERC20 token contracts. So all those contracts are vulnerable to integer overflow issues. And we had source code. We know they were attacked. So basically this gives us kind of a ground truth data set here. So what we did to evaluate EVMPatch was we compared it with a manual patching approach. So we patched all those contracts with SafeMath, a common safe integer library. And we ensured that EVMPatched contracts prevent the same attacks as the SafeMath patch contracts, and that they have the same behavior as the original contract, except for attack transactions. And we found that EVMPatch contracts have comparable overhead to source level patches with SafeMath. We also evaluated the practicality of EVMPatch. We computed the worst case additional costs due to the gas overhead introduced by the rewriter. So for example, here we have a per transaction overhead in the worst case really of $0.01. And per upgrade we had in the worst case about 20 cents. So this is not really a lot when comparing to a smart contract that might have $1 million or maybe even $10,000 at stake. So that is not really a lot. Additionally, we performed a developer study where we asked the developers to use EVMPatch. So we told them to patch integer overflow bugs completely automated using EVMPatch. So this happened very quickly. But we also asked them to write a new patch template for EVMPatch. So the developers had to read a vulnerability report and create a new patch template for a type of vulnerability that is not yet integrated in EVMPatch. And it's really notable here that this took only about 5 minutes on average to patch and deploy a new type of vulnerability using EVMPatch. With this, I'd like to conclude my talk. Thank you for your attention.